Thank you, João Paulo, for the kind introduction. Good afternoon, good evening, or good morning, depending on where you are. Thank you, the organizers of WCNPS 2020, for inviting me to give this talk. And it's my great pleasure to be here and to participate in this conference. Well, I would like to talk about tensor modeling for large array processing in wireless communications. I will turn off my camera during the talk, and I will be back again for questions at the end. Let's start with a brief motivation. We are talking about MIMO channels, MIMO communication systems. This figure gives you a picture of what we are going to discuss. In the general case, we are talking about transmitting signals using different antennas, multiple transmit antennas, which are indicated here. At the receiver side, we receive information also using multiple receive antennas. And in between those two entities, we have the propagation channel, right? In that example here, I'm just illustrating that the information traveling from the transmitter to the receiver, it goes via different paths, right? In that case, we have two main directions, two main waves that are starting here at the transmitter, and they are bouncing on those two scatters and then reaching the receiver. And there is a kind of geometry that we usually consider to parameterize those propagation waves. For instance, for these first lines here, for the first wave, it is characterized by one angle of departure, one angle of arrival, with respect to this perpendicular broadside reference. And we also have tau 1, which is the corresponding time delay, relative time delay that represents the time of travel of this path from the transmitter to the receiver. We have here a second wave or a second propagation path with also its corresponding angles of departure, angles of arrival, and time delay. So that's a basic, very simple representation of kind of parametric channel modeling that we are going to detail later on. Just take one very simple case where you have one single transmit antenna and you receive information in using multiple receive antennas. So in this illustration here, I give you the main axis of information. So we have space, which means that okay, we are receiving the same data, multiple copies of the same data using multiple antennas. We have the time domain, which means that we transmit blocks of data, time blocks of data, and we store and process those blocks at the receiver. And the frequency domain means that your channel depends. I mean, the frequency response depends on the frequency. That's obvious in a frequency selective propagation channel. For every frequency bin or for every frequency point, you have one different gain or one response, right? So in that simple example, we already have 3 dimensions. So this means that we may arrange and model the channel using that. This is what we are going to see next, using tensor formalism that captures these 3 dimensions, right? But if you consider in the second example, if you consider a multiple transmit and multiple receive antennas, and here I am dropping the time domain, right? We still have a 3-dimensional channel representation, but 2 out of the 3 dimensions are, let's say, spatial dimensions, and the third dimension is the frequency one. But we can think about more general representations. If you introduce, for instance, polarization, by using, let's say, dual polarized antennas, then we have this additional dimension, so the polarization dimension. And here, if you see these two kinds of blue here, we are splitting the spatial domain at the receiver into two components, vertical, horizontal. And this is possible, for instance, if you employ a kind of a square or a rectangular array geometry where the antennas are arranged in a plane, right? So you can also split the spatial domain into two components at the receiver, the same way at the transmitter. And here we have overall 7 dimensions or 7 axes where the channel manifests itself physically, right? I mean, the main idea here is to show that, as I said, the wireless channel has a multidimensional nature, and why not exploiting this multidimensional structure that is available, and what are the benefits of doing that? Well, what is a tensor? So an intuitive definition of a tensor is just a kind of 3D arrangement of data or data points. Here I have x, y, z, and I have a kind of hypercube or cube that every element of this cube contains a number, a kind of a data point, and then the collection of those data points make up the cube or the 3D arrangement of data. And as you can see here, using this concept, it's easy to see that a tensor is a generalization of vectors and matrices, right? If we have a one-dimensional arrangement of data, then we are talking about a vector. So we have one, let's say, domain of variation of this data, which is the x1. Then if we talk about a two-dimensional arrangement of data, we are talking about a matrix, right, with rows and columns, and then we have x and y. And that a tensor is can be seen as an extension of these concepts to orders higher than 2. So it can be 3, 4, 5, and any number. It's clear that this is a straightforward way of seeing what is a tensor, right? And we may also talk about a kind of more rigorous definition of a tensor, which is mathematically nicer. We can think of a tensor as a coordinate of another product of vector spaces. And if we take this very simple example where the subspaces, these vector spaces are driven by the unit vectors, right? That have 0 as except in one specific position. So the element of a tensor x can be seen as the coordinate in this product of these 3 vector spaces. And there is another way of doing that. If we vectorize this data cube, we obtain one-dimensional representation of this 3-dimensional array. And that is given by just replacing the outer product by the Canonical product. And in a more general way, we can talk about a tensor as a multilinear map where we just fix 3 bases. In that example, we have u, v, and w. These are bases of vector spaces. And then if we take the combinations, the outer product of vectors of those bases or elements of those bases, and then the tensor is a coordinate of such multilinear mapping. One nice thing about tensors is that is the concept of unfolding, right? Or matricization. So taking again this 3D example of a 3-dimensional array or tensor X, there are 3 possible ways of slicing this cube and organizing those slices into matrices. So these are represented in those 3 illustrations here. We call every way of slicing is associated to one mode of variation or one dimension of this tensor. So here, the one mode unfolding of the tensor is the concatenation of those frontal slices. If you just slice like that, right? And we obtain those frontal slices, we can stack, we may stack those matrices side by side, and we get a flattened representation of this data cube, right? That we call x of 1 in brackets. And doing the same way, using the same principle, but slicing in the different directions, in the two additional directions. So in this direction and in that direction here, we can also form two other matricized versions of this 3D tensor, right? And these are called x of 2 and x of 3. These are the two-mode unfolding and the three-mode unfolding of the tensor x. Of course, if you have more than 3 dimensions, then there are more and more ways of slicing this tensor and organizing the information into matrices. But what is important here is that regardless of the way that you slice this information, the same information that is here is there, and is there. These are different rearrangements of the same information. This is like looking to a cube from different angles, right? From different perspectives. And every matrix here is one perspective or one way of seeing or organizing the information that is contained in the original data tensor X. We also need to define a very useful product, so we know how to multiply two matrices or a matrix and a vector, right? That we learned that in linear algebra courses. And then what is the key? I mean, what should we do if we should multiply one tensor or one cube by one matrix? What should we define? So this is the concept of n-mode product. And we represent the n-mode product by using this cross with an index n to refer to the mode across which we are doing the multiplication. Okay, as you can see here, just look to this figure here. In this case, the tensor x, we are multiplying it, let's say, from the left by the matrix A. So this means that the multiplication of the tensor and this matrix is being carried out across this domain, right, or this dimension. But we may also do the multiplication of the tensor from the right-hand side using the matrix B, or let's say from the third dimension of that tensor using the matrix C. So there are, in this example, there are three different kinds of multiplication. Let's say we may multiply in three different ways, and then that's why we need to specify in the index n in order to be clear in which dimension we are talking about. So the n-mode product between a tensor and a matrix A can be calculated by just unfolding the tensor according to the specific mode n, and then multiplying this unfolding on the left by the corresponding matrix A. And that will give us the corresponding unfolding of the output Y. Remember that this unfolding, this is what we have defined here, right? So you just slice the tensor and then organize those slices in a matrix. And this is the concept that we use here in order to calculate the n-mode product. Okay, what is interesting here is that we can associate n-mode products in different ways, and the order doesn't matter. We can just start with this tensor x and multiply it on the left with A. So using the one-mode product, we get x prime, and then this is the x prime that we get here, and then we apply a second operation, so a two-mode product with B. Then we get x double prime, and the x double prime, we can apply the final operation, three-mode product with C, to obtain the final result. So this is a kind of illustration of this equation here, right? And of course, the final result is the same, although the intermediate results are different, but the final result is the same. So we could very well just swap the order of these operations. We could start with by multiplying x by b and then by c and by a, or any kind of combination will give us the same result. So this is a kind of iterative procedure, multi-step procedure, right? And what is nice here is that this n-mode product is behind the concept of multilinear compression, right? So if we start with a very big tensor X and we define, let's say, fat or wide matrices A, B, C, so the final result would be a smaller version of the original tensor. So if we want to compress this information using appropriate basis, then we will obtain, as the final result of this operation, we will obtain a compressed version or a miniature of the original data tensor. We'll be using this concept later on when dealing with MIMO channel estimation. So let's talk about decomposition. One very popular decomposition is the so-called canonical decomposition, which consists of factorizing or decomposing tensor in a sum of rank 1 components. So every rank 1 component is one tensor given by the outer product of 3 vectors. Right? And here we have a sum of R components that will be necessary to make up the full data tensor X. And this decomposition has several names, but the most popular are canonical polyadic decomposition, CPD, or parallel factor decomposition. And this decomposition reveals the tensor rank. So as you know, for matrices, the rank is the minimum number of rank 1 matrices that are necessary to yield that matrix. In a similar way, the tensor rank is also the minimum number of rank 1 components that need to be summed up to perfectly build the original data tensor X, right, in a combination. So this decomposition is very popular, has been used in many applications, including that of MIMO communications and modeling of MIMO communication systems, and we are going to see some examples of that. Just some more information about this famous decomposition, the CPD, is that if we consider here a tensor of dimensions I times j times k, and we have R components, so the rank of the decomposition is equal to R, we may ask how many parameters we are talking about here by using this decomposition. So the number of free parameters, if we just sum up how many coefficients we have in this decomposition, so every rank 1 term here has I plus j plus k. And then if you have R components, what you get at the end is I plus j plus k times R, right? And this, now compare this decomposition with the number of elements of their original data. So how many elements does this tensor have? So if the number of elements is given by the product, I times j times k. And for moderate or high values of ijk, this decomposition provides a way of representing the original tensor with a much smaller number of coefficients or parameters, right? Just take an example. For instance, if you have 10 by 10 by 10, then we have 1,000 elements in this tensor. And if you have, let's say, a rank equal to 4, what you get at the end is 10 plus 10 plus 10. That makes 30, right? 30 times 4 is 120. And 120 is much smaller than 1,000. So in some examples, we may get orders of magnitude of complexity reduction if we resort to this decomposition. And here I provide an illustration of the CPD using the concept of n-mode product that we have seen just in the previous slides. Using the n-mode product concept, the tensor X, the CPD of the tensor X can be seen as the n-mode product of an identity tensor of rank R, which we represent here. So this identity tensor is nothing but just zeros except this main diagonal, which contains ones. And then if we take the one-mode product with A, two-mode product with B, and three-mode product with C, then we get the tensor X. So this is a kind of illustration, an alternative way of seeing the CPD of a tensor. Well, so let's start with the one application of that on which we worked for some time, is that of modeling and estimation of MIMO channels, right? So just consider this parametric or geometrical model for the MIMO channel. So again, remember that we are assuming here multiple transmit and multiple receive antennas, and we transmit information across time and frequency. The channel is a function of the time. It varies with time, and it also varies with frequency. So the big H here represents the MIMO channel at a certain time instance and at a certain frequency bin, right? So it has two independent variables that across which the channel varies, right? And we are assuming that this channel is a superposition of NP waves or NP multipaths, right? And every multipath has an associated angle of departure, angle of arrival. So the theta t and the phi t are the azimuth and elevation angles of departure, and theta r and phi r are the corresponding elevation, azimuth and elevation angle of arrival, right? And we have inside this exponential the Doppler shift that characterizes the degree of time variation of this, the time selectivity of this channel for a certain path. And we have tau L is the time delay and of the corresponding path, right? And this is, of course, the frequency. And every path is modeled by, has a one attenuation coefficient, alpha L. And this is a very popular representation for a geometrical or a parametric channel, a MIMO channel H, right? What is interesting is that if you look here, we have the spatial domain at the receiver, the spatial domain at the transmitter, but we also have time and frequency. So we can indeed recast this equation, this model, using the tensor notation. And this leads us to a 4D or a four-dimensional tensor, which has rank equals to NP. So the rank of this tensor here corresponds to the number of paths traveling from the transmitter array to the receiver array. And using now this n-mode product notation, we may express the channel tensor as in this form, where the factor matrices now are AR, AT, these are the steering matrices, right, that collect the array response vectors of the different paths, AR, AT, and then AD stands for the time variation of the channel. So this is the component that depends on the Doppler shift, nu, and then AF is the component, is the response that depends on the time delay of the multipaths. So clearly here, okay, now we have a way of writing or modeling the matrix, the channel matrix, but now if we get together time and frequency, then we have a tensor. But what is the point of that? What is the gain of using such representation? We are going to see next, but I can put forward some features, right? So one of the advantages of using this representation is that we can explicit doing signal processing on every dimension separately. By working on the appropriate unfolding of this channel tensor, we may see and we may filter out the response of the channel in different ways. But let's go a little bit farther away if we just consider now that we have uniform rectangular arrays. So we may split the steering matrix AR and the steering matrix AT into other two matrices. So this is what we do here. If we just translate the angle domain into the spatial frequency domain, we may express the steering matrix AR into as the Cati-Rao product of the two corresponding matrices in the vertical and the horizontal domains for the spatial frequencies mu r1 and mu r2. And doing the same thing at the transmit side, we may expand. So starting with this expression and now expanding the AR and the AT into the corresponding spatial frequencies, now we have two additional dimensions, right? So we have two dimensions at, two spatial dimensions at the receiver, two spatial dimensions at the transmitter, delay, Doppler and delay. So that means in total we have 6 dimensions. And finally, by assuming dual polarized antennas at both transmitter and receiver, including the polarization, we get the additional 7th dimension that we call here bipole. This is a matrix which stacks all the co and cross polarized responses, vertical and horizontal polarizations. We can just stack all the combinations and get the 7th dimension bipole. This leads us to a more general multidimensional notion of this channel, where now we have two spatial dimensions at the receiver, two spatial dimensions at the transmitter, and time, frequency, and polarization, right? Of course, when expanding those dimensions, we have more complex representation, right? But at the same time, we exploit more dimensions that are available in your wireless channel. So there is a kind of trade-off between how far you go on by expanding the channel in different dimensions, and what is the price to pay in terms of complexity to manipulate these representations and to devise algorithms for that. Yeah, so one important point that I would like to highlight is that, many works assume kind of IID or IID rate scattering Rayleigh fading channels. So we just draw randomly. If we come back here in this H, so we just draw randomly H from a normal distribution, complex Gaussian, unit variance normal distribution, and this is your channel. But one thing that is important to bear in mind is that now, especially nowadays, we are going to higher frequencies where there is more available spectrum, and especially in millimeter wave frequencies or even in terahertz frequencies, this assumption of IID elements, they don't hold at all, okay? And then we should ask ourselves, okay, is that realistic to work with IID approach? So certainly not. And this means that we should better use those geometrical models for representing the channel. So we should stick to the parameters, so angles of arrival, angles of departure, delays, and having a more kind of complete description of the propagation phenomena. This would be very important when considering higher frequencies and then dealing with MIMO communication design or antenna design or any kind of signal processing that you are going to apply, such as channel estimation and beamforming techniques. Working with IID channels will not hold anymore. And this is the importance of dealing with such kind of parametric channel models, right? And again, by dealing with tensor representations, you get the most of the benefits by just expliciting the different dimensions and then working, and then you can maybe act on those dimensions separately, and this gives you a more interesting view of the algebraic structure of your channel. right? So when we talk about structured channel models, where we have this parametric description of your channel, then this means that what you get, in fact, is a sparse representation of your channel. If you you may transform the description of your channel H, in this case the channel tensor H, you may represent it in a convenient way in terms of fixed bases. So AR, AT, and AF represent fixed bases. And then what you get as the core tensor is a sparse tensor where every non-zero component means that there is energy coupling between a certain receive direction, a certain transmit direction, and a certain delay or frequency, right? This kind of sparse representation is very, very useful when working with millimeter wave channel models or even terahertz channel models where the propagation mechanism in the scattering is very poor. So the waves that travel from the transmitter to the receiver, they reach the receiver via a very few number of paths because of the high attenuation of the medium. And then what you get, mathematically speaking, is a kind of representation of this kind, where you have very few components that are non-zero. This means that instead of working with the big guy, the big channel tensor H, let's work with its sparse representation, right? But for that, of course, we need to have valid and accurate bases. So A bar R, A bar T, and A bar F should be dictionaries. They are dictionaries or bases that define the axis, and then once you have accurate and, let's say, a valid basis, then you can work on the let's say compressed version of this channel H, right? What I show here on the left hand side is just a traditional way of doing compressed sensing, of working with this. Suppose that you vectorize this channel tensor, applying the vec operator, right? So what you get is a very long vector H, small h, right? And these three bases, they are mixed up here in this very big matrix that I call A bar RTF. So this is a kind of combination of these three colors, these three bases. And on the right-hand side, you get a long vector, but that has a few non-zero components. And this is nothing but the vectorized version of this core tensor, this kernel tensor here, right? So what is better to do? Should we use solve the problem by resorting to the representation on the left? Or should we preserve the tensor structure and using the representation on the right? So there are pros and cons of each alternative. When it comes to complexity, if your processing is limited by complexity, depending on the dimensions, let's say on the number of antennas at the transmitter, receiver, the number of frequencies or time blocks, the dimensionality of this vector may be huge, very large. Although the number of non-zero components that you get here is very small. And then depending on the kind of algorithm that you use, a compressed sensing algorithm, for instance, the complexity involved in any kind of algorithm may be very high. And using the representation on the right usually provides you, let's say, more flexible and less complex way of estimating these non-zero points here. So defining the parameters of your MIMO channel. And although we may lose in optimality because the iterative procedure that is behind those algorithms, they are suboptimal, right? So there is no magic here. If you want to go for optimality, you may use the representation on the right. if you really want to reduce the complexity, then it's better to exploit the multidimensional structure and using the representation on the right. Although I should say that the performance of those approaches may be very close depending on the kind of scenario that you have, right? In some cases, we don't lose too much in terms of performance by solving the problem on the right in a tensor fashion, but you greatly reduce the complexity. I would like to highlight two works that discuss very nicely what I have been talking in the previous slide. So this is a work published in 2010 that establishes a link between compressed sensing and the problem of channel estimation, of multipath channel estimation. And this is a more recent work that was published 3-4 years ago, where that in fact discussed the context of millimeter wave communications. And again, this work borrows some tools that were introduced in this first work. By getting some inspiration in those works, in a recent work, we have developed in our group one tensor-based channel estimation scheme for massive MIMO FDM systems. This is a joint work with professors João Paulo Costa and Rafael Souza, where we have shown that channel estimation for massive MIMO OFDM systems can be carried out using hybrid analog digital architectures resorting to a tensor compressed sensing formalism. I will briefly talk about the system model here. We are considering a hybrid analog digital architecture where we have radio frequency beamformers at the transmitter, at the receiver, and we have the baseband frequency-dependent processing at the transmitter and also at the receiver. These are illustrated by those matrices. And when you don't know the channel, okay, you don't know the channel G. So this is our goal. We want to estimate the channel G. And of course, for doing that, we should transmit some pilots that we represent by this matrix X0. This contains the pilot sequences. And we should, of course, use precoders and decoders, so beamforming at the transmitter and also at the receiver to transmit these pilots to different directions. Since we don't know the channel, so there are multiple ways of transmitting those pilots. We may beamform in different sectors, or we may just randomly draw beams and then send those pilots to the receiver, which again use its own beams to capture those pilots, right? And then at the end, what you get is a tensor Y, three-dimensional tensor Y, that contains the received pilots. So our goal is that, okay, by using this received tensor Y, estimate the parameters that make up the MIMO channel G. And what we have shown in this paper is that we can indeed model the received pilots in the Y as a third-order tensor, a 3D tensor, that can be represented using the N-mode products in this form. So we get the channel is indeed the core tensor of the Tucker decomposition, and the Q is the received beamforming matrix. The X0 times W is the beamforming pilot matrix, right? Because X0 is the pilots, and then since we apply W to beamform those pilots, then we get a beamformed pilot matrix here. And the third factor matrix F is the subcarry allocation. And I have here a figure that shows how you can structure this matrix F by allocating the pilots in the time frequency grid. This is one possible way of doing that. There are different ways of allocating the pilots, right? But in this paper, we have used this type of structure, right? So what is nice here is that once you fix your beamforming at the receiver, Q, the beamforming at the transmitter, and you have the non-pilots. We also fix the subcarrier pilots allocation. What you get at the receiver is a kind of sampled version of your channel. So what we are doing indeed here is sampling, is a multidimensional sampling of your channel tensor G. And this multidimensional sampling is achieved by drawing beams at the receiver, at the transmitter, and also by allocating the pilots according to different frequencies. So this is a way of sampling or sounding your channel G. I have an illustration that maybe help understanding what we are doing. So let's just consider the figure at the bottom of the slide here. So we have the channel G, and we can mathematically represent the training period using this illustration. So this is the channel, the MIMO channel. So we have the three dimensions here are the space domain at the receiver, the space domain at the transmitter, and here this is the frequency domain, right? Because we are talking about a MIMO FDM channel. And then what we are doing when drawing beams here at both sides and using pilot allocation on the subcarriers, what we are doing is sampling or compressing this channel using those bases, Q, X0 times W, and F. And this yields a compressed version of this channel that we are calling here pilots, the received pilots. And these pilots, they have dimensions LR. LR correspond to the number of RF chains, radio frequency chains at the receiver. This is the number of outputs that we get here in this beamforming scheme. TP correspond to the number of time blocks or the time span of your data block, and FP correspond to the number of pilot frequencies or pilot subcarriers that we are using, right? So as you can see, the received signal using this kind of scheme here is a tensor that is nothing but a compressed version of the channel, right? And now moving to the figure on the top, as we have discussed before, using the parametric description of this MIMO FDM channel, we can model the channel G or decompose the channel G, the channel tensor G, in this way, where we may impose fixed bases AR, AT, and AF, okay? And we have in the middle a core tensor that has a few non-zero components that correspond to the main scatters or the dominant directions of propagation. Just as a very specific example, if you think about a line of sight channel where we don't have any scattering, any reflection, in the line of sight case, what you get is one single non-zero element in this channel tensor, right? Because there is only one direction, one component. If you have a line of sight plus a reflection, then we get two components, two non-zero components, and so on and so forth, right? So depending on the propagation environment, we may have let's say a sparser structure or a less sparse structure in this kind of representation. And then what we are doing here is by identifying the channel and the received data using this tensor formalism, just plug this decomposition inside here at the bottom, right? If you just plug this description here, then we may arrive at the following expression. So this is a compressed 3D tensor measurement model where Y is given by N-mode products on the virtual channel HV, which is this guy here that has those non-zero components. And these are multidimensional compression matrices or multilinear compression matrices that will compress the channel leading to the received pilot's Y. We can link this representation to the concept of Kronecker compressed sensing that has been introduced in this work. If we just vectorize the tensor y, then we can write as an alternative way of writing this decomposition using the Kronecker product formalism. Then we get at the end this classical Kronecker compressed sensing model based on which we can use different algorithms to estimate the HV here, right? But in that work, what we did, indeed, instead of using the vectorized form of the channel, we opted for the tensorized version of it, so that we preserve the tensor structure and the multidimensional nature of the channel, as I said. And what we can have here in terms of complexity is a reduction which is significant. So I have just highlighted here, if we use the traditional vector compressed sensing approach, then we can bound the complexity by the product of the number of RF chains, LR, to the power of 3, times the length of the pilot sequence to the power of 3, times the number of pilot subcarriers to the power of 3. So all of those dimensions, or all of those resources, pilot resources, they are to the power of 3. And they are multiplied, right? This is the most important thing. And when applying the multidimension, the tensor compressed sensing approach, by operating independently and separately on every dimension of your measurement data model, what you get is a bound on this complexity, which is in fact the sum of those resources. So we have LR to the power of 3 plus TP to the power of 3 plus FP to the power of 3. So what we are doing here is exchanging the product by the sum. And depending on the value that you use for the number of RF chains and the pilot length and the number of pilot subcarriers, you can get a significant reduction on the complexity of your compressed sensing problem. I have here selected just a couple of results to go very fast on them. We have simulated a system with 64 transmit antennas, 4 receive antennas, using 32 RF chains at the transmitter, let's say the base station, and then 2 RF chains at the user, the receiver being here represented by the user terminal with 2 RF chains. And using 1024 subcarriers, from which 256 are transmitting pilots. And we have the length of the pilot sequence is 32, okay, which is exactly the number of RF chains at the transmitter. We have 2 scenarios. So what we want to, the main message here that we want to pass is that if we consider a sparse channel with only 8 paths, or only 8 reflections, or 8 directions, what we have here in green and yellow are 2 variants of the proposed algorithm, which of course we don't have time to detail, but all of them exploit this tensor formalism. And then we get here complexity, NMSC, which is very close to the MMSC estimator that, of course, assume here the perfect knowledge of the spatial covariances, all the covariance matrices. So this is a kind of lower bound to our method. So for lower SNRs, we get worse performance, but as the SNR increases a little bit, then we can achieve the performance very close to the MMSC estimator. And on the other hand, when we increase the number of paths, so the channel becomes less sparse, then of course our method is not so good. So this means that this kind of approach works better for channels that are very sparse, which may be the case in millimeter wave or in terahertz frequency bands. Okay, so it's time to wrap up. I would say that tensors are very powerful tools for modeling and for signal processing in the context of wireless communication, and more specifically in the context of MIMO wireless communications. We have been working on that for more than a decade, and there have been a number of models and algorithms that we have derived to address a number of problems, not only channel estimation, but also semi-blind symbol estimation, space-time coding, space-time frequency coding. And so there are a number of examples where tensors can be used, and they have demonstrated to be very useful for this kind of applications. And more related to the context of this talk, we have seen that working with tensor modeling for large-scale array processing, MIMO array processing, the main thing is that this tensor-based formulation reveals what we call structured sparsity and or structured low rankedness of the MIMO channel, and this structure is lost when we vectorize or matricize the channel that is by nature a multidimensional array. Another point that deserves some remarks is the point of beamforming. We have not addressed in this talk the beamforming design problem. There are some works we have carried out recently. What I can say is that the same principle of tensor modeling could also be extended to the design of the beamforming. So, and we can achieve significant complexity reduction by resorting to what we call multilinear beamforming or tensor beamforming. And that is very useful when dealing with large-scale array processing. Well, what lies ahead for in terms of research directions? I could say that the exploration of block sparsity, off-grid problems when we don't know exactly the basis of the associated compressed sensing problem, then also working with multilinear basis tracking solutions using tensor-based dictionary learning principles is an interesting topic. It's also important to highlight that hardware imperfections cannot be neglected, especially in large-scale array processing, such as phase noise or carrier frequency offset, array calibration. So all of these problems are realistic issues that could be incorporated in our tensor models. Indeed, we have been working also on that. We have suppressed that due to lack of time, but it's also possible to incorporate some of those hardware imperfections and then devise more efficient and also realistic models. Another interesting point is that of distributed tensor-based estimation. So all of these algorithms, I mean, although we get complexity reduction and modeling flexibility by using tensor-based approaches, we could also think of deriving distributed algorithms that could be applied in distributed massive MIMO setups. And this is another track that is interesting to address. That's it. So thank you very much for your attention and patience. And I am available for any questions and comments. Thank you.